So this is the third video. Hopefully it will be as reasonably short as the first two. It's only going to be concerned with something called NMR. It is the sine qua non. It is the gold standard of analysis in modern organic chemistry. There's an old cliche that when the NMR breaks, everyone just goes home. Because if you can't analyze things, you can't do organic chemistry. So in this laboratory, we're going to be looking at two types of NMR. One, where we're looking at protons, hydrogen, and one where we're looking at carbon. Now, there's a couple of rules that I'm freehanding here, freestyling, so I will do them in the wrong order probably. But a couple of rules exist for NMR. And the first one is that it sees odd numbers of nuclear particles. Remember, this is called nuclear magnetic resonance. So we're literally looking at the spin of a particle, and what we're going to do is impart energy. When that energy is of a certain frequency, the spin will switch to a higher state, and then after it's been energized, it decays back down. And when it does, it gives off a quantized amount of energy. And that energy can be captured and analyzed. There's a mathematical transformation called a Fourier transform, which will turn this decay back to a ground state, a term you heard in 113. And that decay will be analyzed and turned into information. So that's what happens. And it only happens with odd numbers of nuclear particles. And that's great for protons because, well, hydrogen has, one proton, one neutron, one electron. That's actually heavy hydrogen. A normal hydrogen, the vast majority of hydrogen is one proton with an electron spinning around it. So 100% of protons get analyzed by NMR. However, for carbon, it's a bit more problematic because carbon has 6 protons and 6 neutrons for the vast, vast majority, 99% of its isotopic reality. And so only 1% of it has a different isotopic mass. And we're going to analyze that. And so we'll look at carbon 13. We've heard of carbon 14, a very heavy isotope that's used in carbon dating. This is carbon 13, so 6 protons because it's carbon, and 7 neutrons. And that's only a very small amount of the carbon. So we're going to take a very small amount of carbon, dissolve it in a non-resonating sample. We should talk about that. And then we're going to analyze 1% of it. So you're going to get lot more information from proton NMR than you'll ever get from carbon because, carbon just doesn't resonate, doesn't exhibit any peaks unless it's that 1% that's the heavy isotope. So what do we do? Well, we need to have our sample have an odd number of nuclear particles. We need to have our solvent have an even number of nuclear particles. This isn't so bad when we use something like chloroform, but we can have chloroform with hydrogen in it. Chloroform is CHCl3. So we want an even number of hydrogen particles. We use deuterated chloroform. Deuterium has 1 proton and 1 neutron. It's hydrogen with an extra neutron, so it's got an even mass in its nucleus. So in carbon, well, that's even. So, using a deuterated solvent, we can analyze it by NMR. So let's talk about what we see in proton NMR. Basically, what I want you to know is that when you look at your NMR spectrum, and you will get a proton NMR, there's proton, and a carbon-13 NMR. Notice both odd numbers of nuclear particles. In carbon, we don't get much information, but let's talk about hydrogen. We get 4 types of information. I'm using the wrong words. What do I mean? What I mean is, let's take a famous molecule, ethanol. Most people just talk about NMR in terms of ethanol. So what we see there is 6 hydrogens, so 6 protons. And what I'm saying in part 1 is these 3 are identical. They're spinning around as a tetrahedron. These 2 are identical. They're in a tetrahedral geometry. They're spinning around. And that one's separate. So in this particular molecule, here there are 3 types. I know types is probably the wrong word, but 3 types of protons. What else do we learn from proton NMR? We learn what's an N? How many are there of each type? In other words, how many are in this far left type, that tetrahedron? Well, I see 3 H's there. How many are in this type? Well, they're identical in the tetrahedron. There are 2 there and there's 1 there. So we have 3 types of hydrogens in this molecule. And we know that there are 3 and 2 and then 1 hydrogens in each one. So ratio here is 3 to 2 to 1 for those 3 types. This is referred to as, like mathematics, the area under a curve. When they first had NMR, they would get the scan out and literally cut out the pieces of paper and weigh them to find out what the ratio of area under those curves were. Integration, area under curve. So we can get the integration, and that's what smart organic chemists like you and I refer to. What's the integration? Next thing is how deshielded. So what do I mean by deshielded? Well, let's get a different color here. This OH, the OH on the end, the hydroxyl of this alcohol, is a very polar bond. And in fact, the carbon in oxygen is also a polar bond. That's a S plus, and that's an S plus on both sides of that oxygen. And what that means is that for the OH bond, the electrons are over there. It would be almost more accurate to draw it like this. It's a covalent bond, but it's very polar. The electrons are pulled off the hydrogen. That poor hydrogen, which was, after all, originally a proton with electrons spinning around it, Now that electron's all the way over with the oxygen, it's just an exposed proton. It has been deshielded. Now, the more deshielded, the greater the electronegativity, the pull from neighboring atoms, the more deshielded it is. We'll talk about what happens when it's deshielded. So, this is very deshielded. So very deshielded proton. Kind of deshielded, right? So if those electrons are being pulled that way, they're also being pulled off these hydrogens. By the time you get all the way over here, are they really deshielded? Not so much. So last thing we learned, well, let's just talk about these first three. So we know that there are three types of hydrogens. They're in a ratio of 3 to 2 to 1. So we have this x-axis, and it's more or less on a 14-point scale. It doesn't really matter about why the scale is what it is. That's not very good, but whatever. So in this particular molecule, we have three types of protons. We could say with a ratio of 3 to 2 to 1. So now, the 1 is the most deshielded. If it is deshielded, it gets dragged to bigger numbers. Right? We call that downfield. So we have this integration of 1. So the area under that curve would be 1 hydrogen. And then the next most deshielded, it has a ratio of 2. And then the least deshielded, has a ratio of 3. You can see that the area under these curves is about 3 to 2 to 1. So what do I see on the scale? I see three types of protons. I see that they have a ratio of areas, ratio of number of protons of 1 to 2 to 3. And by the way, it could be 2 to 4 to 6. It just tells you a lowest integer ratio. And I see that whatever this 1 is, it's pretty deshielded, or it's relatively deshielded. Now, one more thing to talk about, and that is number 4, the N+1 rule. This Fox is the best of us. Let's get the proton of the ethanol molecule here. What the N+1 rule has to do with is the splitting of a molecule. What do I mean? So we had this graph before. 1, 2, 3. What I wanted to do is split any carbon with protons on it by 1 more than you see. So this one has 3 protons on it, N+1 equals 4 P's. This one has 2 protons on it, so N+1 equals 3. That is not a carbon, so it doesn't split, so it's just 1. Here's how it will look on your NMR. Well, the 1 stays 1, becomes sharper. The 2 is now split to 3. It'll be in a ratio of about 1 to 3 to 1. If you see that, remember the integration tells you how many different types how many of each type of proton there is. Here's one type. Here's the second one. Now, this one with 3 hydrogens is going to be split into 4. It's got an image like this. Split into a 1:3 to 3:1 ratio. 3 types of protons, integration 1H to 2H to 3H's, and then a splitting of n+1. Now, that's all the kind of stuff that NMR tells you. You can take a course in NMR. You literally can take a course in this study of NMR. So it's very dauntingly complex, and this is a hard way to try to assimilate all that information. I will say, remember that you only get 1% of carbon. You know what carbon tells you? How many different types of carbon there is in your molecule. It doesn't give you integration. It gives you something about how de-shielded it is, and we can say something about what type of carbon it is, carboxylic acid, alcohol, that kind of thing, by how shifted on the x-axis it is, downfield to bigger numbers, upfield to lower numbers. But basically what you can tell from carbon is how many unique hydrogens there are. What I mean are carbons there are. What I mean is that all you can say from carbon NMR is, let's say you have those 2 carbons you see there are identical, right? If I flipped it over, you wouldn't know that I did it. This one has 2 CH3s on the end that are the same, one in the middle that's different. So you would have 2 types of hydrogens. Those 2 are different, but so the outside ones are the same, the CH3s, the inside ones are identical, right? For this one, the outside ones are the same, the inside ones are identical, 2 peaks. This is where it gets interesting. There are 6 carbons here. Only 1 carbon is next to a chlorine. So that's 1 type of carbon. There are 2 that are 1 away from chlorine. So that's a second one. There are 2. There are 2 that are 2 away from carbon, and there's 1 that's 3 away from carbon. So this one would have 4 peaks. You know what? It sounds complicated. With experience, it wouldn't be so bad. We're going to get some of that experience. And then if you take organic chemistry, you'll hear, a whole hour-and-a-half lecture on this, and lots of practice problems and quizzes and then exams, and it's pretty intense. You have to learn it eventually in organic. So this is a good introduction to it. And I wish I was in your presence. I could discuss this with you in more details. But that's the outline. Watch the Professor Dave video. He's really good. And I hope you enjoy this laboratory. So for questions and anything you need from me, please don't hesitate. Thanks.